you have learned about gas laws, and your page might not look just like this, but you can use pressure and volume to make predictions, and volume and temperature, and pressure and temperature, and volume and the amount of substance. And you know what some of these units indicate. But did you notice pressure is here and here, volume is here and here and here, temperature is here and here? These seem very interconnected. Couldn't we put them all together into one giant ideal gas law? Yes, we can. Thank you for asking. Before we do, though, you are going to need some papers. We're going to need this paper to go on page 68, so you can go find that paper. 69 is where you've been doing your practice problems, numbers 1 through 10 over here. 70, this is the metric system. This is our prefixes. All right, so you're going to need to go get this page. It's got some practice problems on the inside. You should already have this page. In another video, I showed you some examples here. And 72 is blank for now. Dun, dun, dun. And on 73, you should have this page, Practice Kinetic Molecular Theory, and it folds up just like this so you can see the directions either way. So go get that page for 73, that page for 70, and the page for 68. And pause this video and come on back. All right, my dears. So I taught you unit conversions because it turns out they matter a lot. All right, because if you're given just a random different unit, well, we want to be able to convert all these units from one to another so that you can communicate with people that are using different units than you are. For example, if I measure my pressures in torr, well, what is that in atmospheres, which we mentioned previously? So atmospheres is a measurement of pressure, so our torr. And this does not include every single one of these conversions, so you might occasionally have to look one up. So that's not what I wanted. Where did I want? Well, we'll just do it here. I was looking for a GIF for somebody, but here we go. Atmospheres to torr. You can just type that in, and it will usually give you a nice conversion right there. So let's add this to our paper. Okay, we're going to make ourselves a little column right here. Pressure. We know that 1 atm, which is an atmosphere, is equal to 760 torr. And these are important because then we can convert in between and solve a lot more problems because we have a common language. These units are language. They tell us basically what we were measuring and what we can do with it. So you've done questions 1 through 10 at this point. If you haven't, go back, finish them up. But these are a little bit more complicated, and they involve you needing to know a little bit more about the metric system and a little bit more about units. So first, let's take a quick look here. Okay, these are the metric prefixes. For example, whenever you see kilo, it means you've got 1,000 of something. Whenever you see mille, it means you have 1,000th of something. So there are 1,000 millimeters in a meter, and 1,000 meters gives you a kilometer. So what I'd like you to do is use this to work through some of these first questions here. And you'll be doing these, most of these can be done in your head. Many of them will need this, and some of them might need to be done with unit conversions. But you've got answers at the bottom. I want you to figure this out. So pause, do a little bit of that. And these are all base units. Okay, all of these things we're talking about, seconds, meters, grams, Kelvin, these are all base units. But sometimes we might need a derived unit. Okay, a derived unit is something like volume. Volume is length times width times height, right? Length times width times height. But length, width, and height are all measured in length. So that would be meters times meters times meters, and that would give us meters cubed. Okay, a cubic meter. That's not a super convenient measurement, though. We could do, let's see, we could do a centimeter times a centimeter times a centimeter, and that would give us a centimeter cubed. This is about as much as a single die, a dice, one of a pair of dice. And this is about as much as it is in your bathtub. Neither of these are super convenient. So another option we have, this, a centimeter cubed, we call a milliliter. And if you have 1,000 centimeters cubed, you have a liter. And this is what we usually use to measure volume, a liter. It's a derived unit. It's literally 1,000 of these. Okay? So 10 centimeters times 10 centimeters times 10 centimeters, you'll get a liter. All right? The reason I show you this is we use these standardized systems of units in science so that we aren't measuring all in different languages and creating problems for ourselves. So seconds, meters, we measure temperature in Kelvin. I'll teach you more about moles later, but moles is a way of measuring a number of things, kilograms, etc. You'll need to know these for the ideal gas law. So let's jump in. When you did Boyle's law over here, and Guy Lusac's law, and Charles' law, and Avogadro's law, it didn't really matter what units you used as long as they were the same before and after. But that's because the units were canceling out. Torrs over here and torrs over here would cancel out if you did the math. Liters and liters, or milliliters and milliliters, as long as you were using the same one, and as long as it was Kelvin for temperature, it pretty much all worked out. That will not be true for the ideal gas law. For the ideal gas law, we need to be pretty careful what units we're using when we put all of these units together into one giant equation. So let's take a quick look at how we can put these together and what we can do with it once we do put all of these different things, all these different variables together. So what we're going to add here is an ideal gas law. Once you assume all of these things, you have what we call an ideal gas. It's sort of like the perfect scenario. And that means we can make a pretty simple compared to how complicated individual gas molecules are. We can make a pretty simple way of relating pressure, volume, temperature, amount of gas, etc. We call that the ideal gas law. Okay. Of course, it's got to be pretty. And the ideal gas law says this: pressure times volume is equal to the amount of the substance times this mysterious constant that we call R times temperature. That's the ideal gas law. Excuse me. So what does that mean? It means that if you know the pressure and the volume and the amount of a gas in an area, you will also know the temperature of that gas. If you know the temperature of the gas and how much you've got and how much space it takes up, you will also know the pressure. If you know the volume and the pressure and the temperature, you can find out exactly how much of that gas you have. So that means if I had a balloon and I was able to measure the pressure inside, the volume, the space it takes up, and the temperature of the gas, I could tell you exactly how much gas was in that balloon. It doesn't sound like a big deal, but it turns out for a lot of different things in engineering, it's an incredibly big deal. People that do weather balloons need to deal with this, but also people that do math for the space shuttle. This even comes into play in medicine. So let's show you what you need to know about this ideal gas law. Let's start with the easy bits. All right, volume is incredibly easy. No matter what, volume is always measured in liters. Okay, and that's a capital L as our unit, so that one's easy. Another one we can check off is moles, or the amount of substance. This is measured in something called moles. I will teach you more about it soon, but for now, can we just put amount of substance? We'll come back to this page. You can just type MO, or you can write MOL, or you can use N as the unit. You can do whatever you like until I teach you more about that. It won't mess with your math, I promise. Another one that I wouldn't say is easy, but is not super complicated, is temperature. Okay, I have already told you, you've only got one option for temperature. Temperature, absolutely, positively, every single time needs to be measured in Kelvin. Okay, and we abbreviate that K. Good news is if you have Celsius and you want to get to Kelvin, it's pretty easy. You do degrees Celsius plus 273.15, and that'll give you degrees Kelvin. So those are the easy ones out of the way. If you are doing ideal gas law work, you absolutely must be measuring volume in liters, which means if it's not in liters, you need to do, where'd it go? Some unit conversions. You absolutely must measure amount of substance, period, and I'll teach you more about how to measure it later, but you can use, for now, you can use grams and grams, moles and moles, some measure. And then for temperature, you absolutely must use Kelvin, no Celsius. It'll mess with your math. That leaves pressure and this mysterious constant. Ooh. So pressure, you've got two options. You may measure pressure in atmospheres, which is literally one Earth's atmosphere of pressure pushing down on your shoulders or on anything. We abbreviate that ATM. But this is very helpful for things in the big wide world, but it's not as helpful for smaller measurements. For those, we use something called kilopascals. And we abbreviate that. Capital K for kilo, which means 1,000, and PA, kilopascals. You can choose either one of these, and you can work in problems in either one of these units as long as you stick to one of them. However, based on which measurement you use, you're going to choose a different constant. That's because this constant is pretty much magic. It's incredible. I'm going to give it little stars because it's so wonderful. It's the thing that makes this math magically work out. This is called our gas constant. It's literally just, let's see, gas constant. It's a number we put in there. And if I'm moving too fast, you can pause this anytime. It's a number we put in there literally to make the math work nicely. All right, that's our gas constant. So if you are working in atmospheres, you are going to use an R value or a constant. You're going to plug this in of 0.082 liters times atmospheres divided by moles times Kelvin. Bonus points if you can figure out why those are the units. However, if you are measuring your pressure in kilopascals, you're going to use a different R constant. You're going to use 8.314 joules per mole times degrees Kelvin. Doesn't matter which one you use, as long as you match them. So if you're using kilopascals, you must use this R. And if you're using atmospheres, you must use this R. So let's draw some lines to connect these. I'm going to leave a little note for ourselves. Match to R. You absolutely must. So, what can we do with this? Oh my goodness, so many things. Let's take a look. We're going to skip. So, just a review of what you should be doing in this unit for homework so far. You have done questions 1 through 10. Let me bring that back here. Questions 1 through 10 on here, and your work should be on page 69. You should do questions 1 through 15 on practicing using or reviewing using the metric system. You've already done the 1 through 6 on here on unit conversions. You should also do 7 through 14. You can stop there. 72 is blank, and that's because 72 is where we're going to put our work for questions 11 through 16. And when you've done all of these, 11 through 16, you're going to come over here, and this is where you're going to put it all together. You're going to do unit conversions and gas laws and kinetic molecular theory, et cetera, all of this belongs there. And I'll have a separate video that walks you through a couple of those, or maybe some worked out problems, we'll see.